In today's class, I will introduce graph embedding and node embedding. So it's a very popular topic that emerged a few years ago, so maybe around 2016. And there are many works on the topic currently, so I thought it was interesting to introduce it. So first, there are several types of embeddings with graphs. We can differentiate the node embedding, edge embedding, substructure embedding, and wall graph embedding. So today I will mostly discuss about node embedding. So the difference between them is that if you have a graph like this one, you can embed it. So if you do node embedding, each of the node will correspond to one dot in this case, for instance, a two-dimensional space. So when you do an embedding, you embed elements in a low-dimensional space. In this case, it's a two-dimensional space. And if I do node embedding, each of the node corresponds to one dot in this two-dimensional space. If I do edge embedding, then it's each of the edge which becomes one point in this two-dimensional embedding. In substructure embedding, I will embed, for instance, here communities. So you see that there is a green, orange, and blue communities, and each of these communities will correspond to one dot in my embedding space. And finally, if I do wall graph embedding, then it's each of the unique graph which become one dot in my embedding space. So of course, this is used to compare several graphs. So for instance, if you have, I don't know, hundreds of graphs and you want to find which one are more similar than others, then you can use this wall graph embedding to see which graph is closer from other ones in this embedding space. So just a vocabulary point, it's that so today I introduced node embedding, but sometimes in the literature you can see it called graph embedding. So people will say I'm doing graph embedding, but in fact it means that each of the node of the graph becomes one point in the embedding space. So in concrete terms, what I'm doing when I'm doing an embedding is that if I do an embedding in D dimension, it means that for each of the node, if I do node embedding, each of the node, I will assign one vector of size D. Okay, so it means that for each node, I will assign D values. And these values, the point is to use them later. So that's one of the usage is to think of each of these D values as a feature of the node. Okay, so for each node, I want to compute a vector of size D, and this vector will represent this node, and it will represent the position in the network. Right? It will represent. It will capture some properties of the network, on the network topology, and so as to represent the position of this node. Okay, so for each node, I have a vector with the elements in it. And the point is that these vectors, they can be used for something. So they are useful for what we want to do with the graph. And we will see that we can do link prediction, we can do node classification, we can do role detection and community detection and other things. So we will see that there are different types of embeddings and that each embedding is capturing something about your graph. And so if you do node embedding, you can also do get a vector for edges by combining the vectors of the nodes. Okay, if you want to obtain a vector to represent the edge between n1 and n2, then you can combine the vectors representing n1 and n2. We will see that there are also two ways of using embeddings. One is with unsupervised learning, in which we are interested really in the distance between the nodes. So you have two vectors, and if you have vectors, you can compute the distance between these vectors. As we have seen in the previous class, you can use, for instance, a Manhattan distance, Euclidean distance, cosine distance between two vectors. But the other way to use these vectors is by supervised learning, as I said, by considering that, for instance, if you have an embedding in 10 dimensions, then each of the dimension corresponds to one feature. So if you remember the previous class on machine learning, we have seen that, for instance, for a node, you can construct a vector with some properties of the node, for instance, some centrality. So you can have a vector representing node N1 with the first value of the vector corresponds to its degree. The second one can correspond to its, betweenness. The third one to the average degree of its neighbors, and so on and so forth. So in this case, you have a vector representing your node, but this vector is composed of manually chosen properties, network properties. And in graph embedding, the point is to create such a vector, but with features that have been automatically created by an algorithm when doing this embedding. So what can we do with embeddings? So we can do all the tasks of machine learning that we have seen before. We can do link prediction, we can do graph reconstruction, community detection, node classification, role definition, which is something I haven't talked about yet. And also it can be used for visualization. So that's really the power of this embedding approach, is that since each of your nodes now is synthesized as a vector, and that the machine learning algorithm are actually using vectors as input, now you can use all the tools of machine learning on your vectors representing nodes of your graph. So let's start by introducing some of the popular methods for graph embedding. So the first family of methods are based on matrix factorization. And they are, some of them are actually quite old. So you see, for instance, the Laplacian game maps, which has been introduced as a general method, not only for graphs, actually. And it was introduced in 2001. And so there are several embeddings like that that were introduced, let's say, in the last 20 years. But the topic of graph embedding became very, very famous and very popular very recently because of all the new works around machine learning. And so people started to really be interested in this possibility to represent all the complexity of the structure of a graph as a vector. So let's start with this method, so Laplacian game map. And the goal is, so we can summarize it in a simple way by saying that it has an objective function that we want to minimize. And this objective function is that we want to find the optimal embedding, such as we want to minimize this formula. And this means that so this part correspond to making the difference between the vectors, the embeddings of the nodes. Okay, so this represents in the final embedding, this corresponds to the vector of node I, and this corresponds to the vector of node J. And so we want to compute just the difference between these two vectors. And we want to multiply it by the value of the similarity between I and J. Okay, so you need also as input a similarity matrix. So a similarity matrix means that I want to have a high value if two nodes are similar, and a low value if they are dissimilar. So for instance, a basic similarity matrix can be to take the adjacency matrix. Okay, so it means that you have a 1 if two nodes are connected, and a 0 if they are not connected. This corresponds to a similarity because you consider that if two nodes are connected, then they are similar. But you can take another matrix, such as, for instance, let's say the common neighbors between nodes. So you compute how many common neighbors there are between I and j, and this tells you what is the value of Sij. Okay, so this is a measure of similarity, and the objective of Laplacian eigenmaps maps is to find the vectors of every node I and j, such as if we sum over all pairs of nodes, the product of the difference between the vectors and the similarity is minimized. And what this means is that if nodes are similar, then they must be close in the embedding. So you get the general idea here, which is that, so if they are similar, they must be close in the embedding. So your embedding is kind of respecting this notion of similarity that you have chosen. But it summarizes it in a small number of dimensions, because you're searching for here vectors of a given size. So you say, for instance, I want to find vectors of size 3 or 100 or whatever that will best summarize my similarity matrix. Okay, so for instance, the adjacency matrix. So we've only now, so for instance, d equals 3, so 3 values for each node, you will have summarized your adjacency matrix. So a question you might ask is how to find actually this solution. And so I won't go into the details in this class. That's not really the topic, but just to give you an example, this is how to find the solution to the Laplacian eigenmap map in an efficient way. So actually, if we take as a similarity matrix the adjacency matrix, then you can write the problem to solve in matrix form in this way, using the Laplacian that I have defined in one of the first classes. And so we have to impose a constraint to avoid trivial solution by saying that that's the sum of the length of the vectors must have a given length, because otherwise you could put all the vectors at 0, for instance, and this will be always 0, and you will minimize your problem in a trivial way. So you have to impose some constraint, and then with this this definition, you can say that so if you want an embedding in d dimensions, then you have to find the d eigenvectors of lowest eigenvalue of normalized Laplacians. Okay, and so since your eigenvectors, each eigenvector has n values, if you have n nodes. So if you have d eigenvector, so the first element of the first eigenvector will be the value of node, the first value of node 1. The first value of the second eigenvector will be the second component of the vector of node 1, and so on and so forth. Okay, so this is so you have to find the eigenvectors of this matrix. So here is a second example of embeddings. It's an algorithm called HOPE, for higher order proximity preserved embedding. And so we still can define it as an objective function, but you see that this time it is different. You still have the similarity matrix S, but this time, instead of subtracting the vectors of nodes in the embeddings, you will multiply a vector by the transpose of the order. So multiplying a vector by a transpose gives you a value. And so what you're trying to minimize is the sum over all pairs of nodes of the difference between the similarity and this value of the product between the vectors in the embedding. So again, S can be the adjacency matrix, number of common neighbors, and so on and so forth. And the idea of this objective function is that as the similarity tends towards 0, then the embedding vectors must tend towards orthogonality. So basically, if the similarity is around 0, so you have very low similarity, then the vectors of the node must be orthogonal. and orthogonal vectors have a value of, when they are multiplied, a value of 0. So the question, obviously, you see that I've presented two different objective functions, and we understand intuitively that they are different, but which one is the best? Well, there is no single answer. It depends on what is your objective. So on this objective function can be understood as really keeping the distance in the similarity matrix, conserving these distances in the embedding, because we see that here, if the value, for instance, of similarity is, I don't know, whatever, it's 10, then we would like the value of this part to be also 10, because we would like to have the same value for the similarity and for this product of the vectors. Since if we have the same or similar value, this part will be close to 0. And then doing the sum of this will allow to minimize the global value. Okay, well, it was different in the previous one for the Laplacian L-game maps. You don't try to have the same value for S for the similarity and for the vectors. It's less direct maybe. While Hope will have a more direct objective, which is to really conserve the similarity matrix in terms of multiplication of the vectors representing the nodes. So let's move to a second family of graph embedding methods, which are random walks based approaches. So these approaches are the most used currently. And let's start with one called deep walk. So deep walk was the first of these approaches, which are using a combination of random walk on the graph and of a simple neural network approach to create the embeddings. So there are many methods that are based on this general idea. So just after I will present node 2vec, but then you have many methods called something 2vec. And all these methods are based usually on this approach, combining random walks and neural networks. So this method actually, so the first one, deep walk, is based on a simple adaptation of something which has been proposed for text mining, which is an algorithm called word 2vec, using a skip-gram algorithm that I will present briefly. So this is a method which has been proposed to deal with text, because actually the problem of doing machine learning with text is quite has similar problems than doing machine learning on graphs. The problem is that you cannot put words in input of a machine learning algorithm. So if you want to do some prediction, some classification, some regression on data, you need to give as input to your algorithm some vectors. But how do you represent a text as a vector? How do you represent a sentence, a word, as a vector? And that's a problem that we want to solve. And it's the same problem with graph. How do you put a graph as input of a machine learning algorithm as a vector? And so the problem for text was, well, not solved, but a solution was proposed with this approach called word embedding. So the principle is that we have a corpus and we read this corpus word by word. So we are reading the sentences word by word. And for each word, we defined what is its context in the sentence. Okay. So for instance, for the word the, here, we will look at the two words which are the closest. So in this case, quick, brown. And we consider that these two words compose the context of the. So we remember somewhere that we will have some training samples that if I ask you what is the context of the, then you answer quick. And a second example, if I ask you what is the context of then the answer is brown. Okay, so we really remember that these words are part of the context of this word. And I move to the next word. So here I have quick, and the context of quick is the, or brown, or fox. And so on and so forth. I continue. So brown has as context these 4 words, and so on and so forth. And I will do this for all the sentences of the corpus, so for all the words of all the sentences of a given corpus. Obviously, so in machine learning, people are taking very large corpus, like for instance, all of Wikipedia, and they make this extremely long list of training samples. And then the objective is to build a machine learning algorithm. So they use some simple neural network approach to train this algorithm. And the principle is that as input, I will put brown. So how to give it as input of a method? So it's in this way. So this is an illustration of a neural network. And the input is in this shape, so that we can call one-hot encoding. So if you have 1,000 different, so in this case 10,000 words in your corpus, then you will have a vector of size 10,000 with only 0 and one corresponding to the position of the word you're trying to represent. Okay, you want to represent. So each word has a unique position. You put this vector as input. Then you put it as input to your neural network. And this neural network, you will train the hidden layers so that the output will correspond to the word in the context. Okay. So if I take the previous example, if I show brown as input, I want here to train my model so that it will give me as an output brown. But so we know that we won't have the right answer, okay? Because we put brown as an example, and we train the model so that we say that the answer should be the, and then we show another example where we have the same input brown, and we want the answer to be quick, and we also want the answer to be fox and to be jump. So obviously, the objective is not to train a model that will actually answer you what is the context, but it will tell you what is the probability for each word that it's in the context of the word. Okay, so the objective is to get the probability that if you randomly pick a word nearby your objective word, then that it is the word in the context. So if the idea is that if a word actually appears very frequently in the context of another one, then when you present this word, it will give you a high value. This can actually, before I presented, I introduced this as a neural network, but actually it's a very simple neural network because you just have here 2 matrices which which are composed of weights, and you must learn the weights of these matrices. So basically, this is my input, as I explained, a one-hot encoded vector, so only one value which is at 1 and all the other one are 0. So when you multiply this by this large matrix, actually it will just select one line here, which corresponds to the embedding that I will have for the word, for this word. So for instance, if this corresponds to the position of fox, when I multiply by this matrix where I have, each of the row corresponds to one word, and each of the column corresponds to one dimension of the embedding I want to obtain. And so the weights I need to learn to train my model is this matrix. So basically, it just means that I want to find the embedding of the words. So this corresponds to the each line of my matrix here corresponds to the embedding of each of the word in my corpus. Okay, so I multiply this by this matrix. I get some value. I multiply it by this matrix, which actually is the transpose of this one. And I get my output values. And I try to minimize the error between the predicted context and the actual context that I'm showing to it that I have obtained by this list of samples. Okay, I'm showing all the samples, and I'm trying to minimize the error between the answer and the right examples from the corpus. So okay, so if you are not familiar with machine learning and neural networks, maybe you don't get all the details. That's not a problem. You're just trying to minimize some error so that you're learning what is the context of each word. And what is interesting, so why not this? Why not this approach? But this was really a big game changer in the field of text analysis because it seems to work pretty well. So the principle is that the vectors that you obtain by doing this are actually embedding some semantic of the words. And for instance, it has been shown that you can do operations on the vectors that you obtain by this process, and that this operation of vectors makes sense. So to give you an example, if you take, so this is the typical example we give, if you take the vector for king, that you subtract the vector corresponding to the word man, and then you add the vector corresponding to the word woman, then you will reach the vector corresponding to queen. Okay, so that's here the composition. You have king, you subtract man, so you get here. You add woman, and you obtain the vector corresponding to queen. Okay, so the principle is that the vectors you obtain this way, they kind of each of the each of the element of these vectors, they kind of represent something. So for instance, you can imagine that the first value will represent something like the concept of royalty. The second one will be the concept of masculinity, or maybe another, the fourth one will represent the concept of age. So of course, in reality, it's much more complex than that. But you can think of it in this way. Okay, so each of the dimension is kind of capturing some semantic of the word, and so that's why if you kind of subtract the masculinity of man to the masculinity to the word king, then you add the femininity or to this word, you will get the concept of queen. Okay, so this is well in theory, but what is interesting is that it's also true in practice. So in this article, they tested that, and what they do is to take, for instance, the word for a country. They subtract the vector corresponding to, so it's capital in this case, and they check what and they add this difference to the word corresponding to another country. So in this case, they can say that in their embedding, Paris is to France as to Rome is to Italy, or Tokyo is to Japan, or Tallahassee is to Florida. And we see that it seems to work. And if you check other examples, so for instance, a scientist is to Einstein, in a similar way that violinist is to Mozart, or painter to Picasso. So you see that it's not maybe exactly true, but nevertheless, it really gets something which seems meaningful. So for instance, I don't know, there are some example like Silvio and Berlusconi, Nicolas Sarkozy and Barack Obama, so seems to work. Sometimes it's a little bit more strange, like sushi is to Japan, to what tapas is to France. So not. Clearly, it's not exactly true. So it's not magic. It's not something that works perfectly in all cases. But nevertheless, you see that you obtain something which is quite close to what you would expect. When you come, so sushi is to Japan, to what tapas is to, you could get anything. You could get Putin, you could get I don't know, Baltimore, you could get Obama, but no, you get so from France you get tapas. So we can see that there is really something actually quite deep and meaningful which is captured by this process. And so because this was so successful, it already became a game changer, as I said, in the field of natural language processing. And that's these techniques that are currently used, for instance, nowadays in Google Translate, or all these things that do, I don't know, so anything that, or if you're using, I don't know, like Alexa or Google Home, these kind of things that try to understand language, natural language, they also are based on this word embedding mechanism. Okay, because this is really a powerful way to manipulate vocabulary and language. So because it was so successful, it was actually the same mechanism was applied to many other different how to say tasks, and this is possible because the algorithm skipgram, which is used here, which is this principle of comparing an element to its context, is actually a generic algorithm that can be applied to other things. So skipgram is a generic algorithm that takes an input, the element to embed, and a list of context. And if I give you these elements to embed and context, then you can apply the skipgram algorithm and it will return you an embedding. Okay, so it's exactly the same algorithm which is used for word, but that can be used for other things. So let's go back to deep work now. And actually, the principle of deep work is just to use this skipgram but on graphs. And how to do that? Well, they generate sentences using random walks. So you start from a node, you do a random walk, and you remember the labels of the nodes that you're encountering. Okay, so you start from node N1. So this is your node of interest. And then you move to random. So you follow the graph and you arrive to N5. So you remember that N5 is in the context of N1. Then you continue to move and you arrive to N10. And so you remember that N10 is in the context of N1, and so on and so forth. So obviously, as for words, you need to choose a size of a context. So how far can you go in the random walk and still consider that you're in the context of your original node? But so following this process, you're generating many sentences. So actually what you do is that you start from every node several times and you do these random walks. So it's like if you were building a corpus of sentences composed of nodes that are close from each other. So you get this corpus, and on this corpus, you apply the skipgram algorithm that I just explained before. And so you get an embedding with properties that you hope are similar to the one we observed for the word embedding and which are very efficient. So you have some parameters, which are the number of dimensions that you want. So you can choose any number. Usually you will choose some small value because you're trying to do some embedding in small dimensions. But small can be, for instance, 100. It's a common value is 128 in the literature when you do embeddings on large graphs. You need to choose this context size, as I said, and you also have to choose some parameters like the length of the random walk, the number of walk you want to do from each node, and so on. But these are more technical parameters. They will have a lesser influence on the results. So this is deep work. So as you see, it's really simple. It's really doing these random walks and then applying an algorithm called skipgram on it to generate these embeddings. But when this algorithm was proposed, it was really a big, how to say, a great innovation for the field of network science, because you really obtain a nice way and simple way to transform a graph into an embedding. So I think the next year, another algorithm was proposed, which is also very famous now, which is called node-to-vec. And the principle is to really keep the same method, but to propose a bias to the random walk, to be able to capture different types of context. So the idea is that instead of just moving randomly in the graph with random walks, we will impose the walk to follow either a kind of a breadth first approach. So the breadth first means that you will try to move in the graph, but first by visiting all the nodes which are close from your starting point. Okay, you have a starting point. If you do a breadth first search, you will move by kind of doing these circles around your original node, and so you will tend rather to stay close to this original node. And on the contrary, if you have a depth first approach, then you will first try to go far away from your original node, and then so you choose an original direction and you explore as much as you can in this direction. Then you will go back and took another direction and explore as far as you want in this direction, then go back, and so on and so forth. So this will correspond to different ways to explore your graph, to do random walks that might capture different aspects. So for instance, with the first one, you will rather capture more the local neighborhood, while with the second one, you will maybe more capture something like the global structure of your network. Okay, so maybe short distance and long distance topology relatively to your nodes of origin. So your context is different in both cases. So just what they introduced compared with deep work is just two parameters called P and Q. And P is a bias towards revisiting the previous node, and the Q is a bias towards exploring undiscovered part of the network. So you have a little illustration here. The principle is that you are currently on V, and you're coming from T. Okay, so the previous hope of the random walks was going from T to V. And then you see that you will have a probability, well, not a probability, but your walk is biased by P towards coming back to the node you're coming from. So you will tend to stay close to where you're coming from. And this Q will bring a bias towards exploring nodes which were not neighbors of where you're coming from. Okay, and one corresponds to nodes that are neighbors of the node you're coming from. So you can rather choose to bias towards coming back to where you're coming from, or going away as far as possible from the node you're coming from. Okay, so that's the meaning of these P and Q. So we have seen that these random walks-based approaches, they are relatively simple to understand what they are doing if we don't go into the details of the skipgram algorithm. But unlike the first approaches in which you had a clear objective function, in this case we have just described the process but not the objective function. Actually, it's also possible to define them in terms of having an objective function. So this will be the one for deep work. And we see that this objective function actually looks quite similar to the first ones. It's also a minimization for the sum of the sum for all pairs of nodes of this formula. And this is, as with hope, you taking the product of the vectors of both nodes, second one transposed, and you subtract this to some value here. So for hope, this was the value that you would find in the similarity matrix. And so just a technical point, so this is the softmax function because we are using a neural network, and this is how the output of this is used to transform the output of the neural network. But it doesn't change much the result. The point here is that you need to understand this part. So this part actually corresponds to the probability for a random walk starting from node I to reach node nj. Okay, so this is the probability for this node to be in the context of this one in terms of random walks. And so this means that exactly like hope, you will try to keep in the embedding, you will try to keep this property. So this means that if this value is high, so for instance in the graph, if two nodes are close in the graph, then this value will be high because the probability to encounter the node starting from the other in a random walk is quite high. So because this is high, then you will try to, since you will try to keep this subtraction close to 0, then you will try to keep this value in the product of the two vectors. So for this value to be of the same, so you want this to be high. If this value is small, then you will try to keep this value small. And to keep this value small, you need the vectors to be orthogonal. Okay, so you need the vectors to be completely different. While if these two, if this value is high, then you will try to have the same vectors here, because in this way the vectors will be parallel and the value will be high. Okay, so just to keep the general idea is that the distance in your embedding in terms of cosine distance or dot product distance, so your distance in the embedding should be proportional to this notion of distance, which is defined by the probability to encounter the node in a random walk starting from the node. Okay, so basically two nodes that are very far away in the graph should be far in the embedding, and two nodes that are close in the graph should be close in the embedding. So why using these approaches instead of maybe using hope with a similarity matrix based on random walks? Well, because the advantage here is that you don't actually need to compute this similarity matrix. And this is important because, for instance, if you need to compute this similarity matrix, you need to compute it for all the pairs of nodes. And so this is in a complexity of n squared, okay? Because you need to compute it for each node n, you need to compute for all the other node n. But in this case, with this approach, you don't need to compute that. You can just do random walks from each of the node. So you will have a complexity which will be proportional to n, even though you have to define the number of random walks and the length of the random walks, but nevertheless, the complexity is much lower for generating this corpus of samples than to computing this n squared complexity here. Let's now say a few words about what are actually embeddings. So we can remark that an adjacency matrix could also be considered as an embedding, but in high dimension. So if you take one row of an adjacency matrix, it's a vector. And so you can consider that the first row of the adjacency matrix corresponds to the embedding of the first node. The second row corresponds to the embedding of the second node, and so on and so forth. The problem of this is that this embedding is in high dimension, and that it's very difficult to to learn from this kind of embeddings in high dimension and that are very sparse. And also this embedding, if you think about it, what does it capture? So it will capture something called the structural equivalence, which means the kind of two vectors are similar if two nodes are connected to the same neighbors. Okay, if two rows of the adjacency matrix are equals, it means that the corresponding nodes are connected exactly to the same neighbors. So we could think of the distance in this embedding made by the adjacency matrix. The distance would correspond to the number of different neighbors. Okay, for each neighbor which is different, you will have a 0 in one vector and a 1 in the other one. So if you compute something like the Manhattan distance, so just the subtraction between the two, for each difference, you will have one, a value of 1. So you're counting how many different neighbors you have. And you see that this kind of notion of defining the distance between two nodes as the number of different neighbors they have is probably not a good way to capture the similarity between nodes. So that's why it's not really meaningful to use the adjacency matrix as an embedding, even if you could solve the problem of high dimensionality by using an algorithm called for a process called dimensionality reduction, like TSNE or PCA, that allows you to reduce the number of dimensions of some data while keeping the notion of distance. So you could reduce the number of dimensions of the adjacency matrix, but you will still have this unintuitive notion of distance between nodes. So that's why it's better to use other approaches like what I presented before. Another types of things we have already discussed, which could also be understood as embeddings, are graph layouts. So if you remember, I talked briefly about the force-directed layout, the Kamada-Kawai algorithm that are used to create plots representing graphs. So you try to put the node in space so that the graph is easy to understand. And this exactly corresponds to an embedding in 2 dimensions with an objective which is defined as, you remember, this minimization of a force-based model in which nodes try to repulse each other, and there are some attraction made by the edges. Okay, so this will define an objective function, which is solved by the layout algorithm. So why not? Probably also this solution is not the most efficient because you're not, for instance, if 2 nodes are exactly similar, they have exactly the same position in the graph. The graph layout usually will tend to try not to put them exactly at the same location because you want the graph to be easily interpretable for a human. While in graph embedding, that's not what you care about. You instead care about if 2 nodes have exactly the same position in the graph, probably you have them to have exactly the same vectors because you want to embed the position in the graph. And also this algorithm for layouts, they are usually not scalable. So that's also a problem because embeddings are usually useful on large graphs. So theoretically, yes, a graph layout is an embedding of a graph into a small dimensional space, but it's not useful for most tasks. So a first application of node embeddings is for visualization. So exactly as a visualization algorithm could be used for graph embedding, well, graph embedding can also be used for visualization. So the problem is that we tend to do embeddings usually in a relatively large number of dimensions, like 50 or 100, So you first need to reduce this number of dimensions to 2 so that you can plot your graph and read it as a human that can only read 2 dimensions. So that's why we use this famous algorithm for dimensionality reduction, like TSNE or PCA. And you use them to reduce your 100 dimension embedding into 2. So while keeping the general notion of distance of your original dimension, 100 dimensions. And so you obtain some visualization. So this is just to give you an idea. Some embeddings obtained in this way in 2 dimensions for click rings. So if you remember click rings, they are composed of cliques of nodes. So these nodes are all connected to each other. And there is one edge connecting 2 cliques, okay? And this forms a circle. So if you plot it using a spring layout, so layout for network visualization, you obtain something like this, which is relatively easy to read and to understand in terms of this click ring. If you use a different algorithm like Laplacian eigenmaps, you get this thing. Exactly as I described before, now all the nodes that are in the click, they will be on the same exact location because they occupy the same position in the graph topologically. So you maybe see that, so you will have all the nodes of the click in the same location, and the 2 nodes which are connected, make the link to the other clicks, they are a little bit to the right and to the left because they occupy a slightly different position in the graph. But you still can recognize this shape of a click ring. This is a result obtained by another algorithm where you see that it's actually quite different because this time all the nodes which are in cliques, they are kind of in the middle because maybe they occupy a similar also position. And the nodes that make the connection between the cliques, they are very far away, right, at the periphery here. And this is interesting because according to this embedding, you're capturing something really different. You will say that even though these nodes are actually not close in the graph, well, they are still close because they kind of occupy the same position in your graph, but in a different way. And this is the result with Node2Vec, and you see that we still recognize the cliques, but maybe we lost a little bit the notion of a circle. But anyway, it's a different representation in which you see that you still keep kind of the structure of your original graph. But maybe it's not as simple to interpret. You can also use embeddings for community detection. This is very simple to understand if you think of community detection as a task of graph clustering. And I introduced in the community detection class what is clustering. So in clustering, you try to find group of nodes which are close from each other in terms of distance, for instance, the Euclidean distance. So for instance, if you take this picture of a graph and you forget about the edges, you just think that these are dots in a 2-dimensional space. And then you think that you're trying to find clusters. And clusters mean groups of nodes which are close in space. And you see that, well, all the blue nodes, they are close from each other, and they are far from nodes in the other groups. So you see that if this is a 2-dimensional space and I apply an algorithm for clustering normal data, not graphs, like k-means or dbScan, so these are algorithms for clustering of normal data, and I apply it on this data in which I have just dots in a 2-dimensional space, then you see that I will detect these as a cluster, the blue one as a cluster, the brown as a cluster, and so on and so forth. And you see that these clusters correspond to the communities I would also find with a community detection algorithm on this graph. Okay, so to take a concrete example, if I go back to this visualization, if I take node2vec and I apply k-means on this, it will probably find a group here, a group here, another one here. So maybe you will have a problem to find all of them, but basically you see that you will find communities that make sense in graph term, because your nodes that are close in the embedding of node2vec, they are also close in the network. And that's usually what you're searching when you're searching for communities in a network. So you see that the two things are related, and that by searching clusters in the embedding, you're actually searching in some way for communities in the graph. So another task that you can do with embeddings is node classification. So the principle is very similar to what I explained last week in the machine learning class. So if you remember, we were saying that we could build a vector composed of features of the node. So before it was, for instance, centralities. And that from this vector, you can train a machine learning algorithm to recognize from the features some property of the node, like, for instance, age, political opinion, and so on and so forth. And so the principle is that now I have actually computed by the embedding a vector for each of the node. And from this vector, which is the vector proposed by the embedding, I can train a classifier to recognize if it's, again, age, what's the age of the person, the political opinion, and so on and so forth. Of course, you can combine. The features obtained by the embedding and some other topological features like degree, closeness, and so on and so forth. So the principle is exactly the same as last week. And there are some controversies on this because they are very recent problems and approaches, but it seems that a method like node2vec is giving very good results in real life tasks to classify nodes, for instance. You can also do link prediction, and you can do it in two ways. So the first one is to do unsupervised link prediction by using the notion of distance in the embedding. So as I explained before, the distance in the embedding should be proportional to the probability to encounter the node in a random walk, starting from the node of interest, and the probability to encounter the other node of interest in the pair. And so we have this notion of distance, and we can use it for link prediction. So for instance, I consider that if two nodes are close in the embedding, there is a higher probability of an edge appearing between them than if they are far apart in the embedding. Okay. And intuitively, we see that it makes sense because it also means that they are close in the graph. They have a high probability to be reached by random walk, which combines some notion of having many nodes in common, not many neighbors in common, for instance, because if you have many neighbors in common between A and B, it means that if you do random walks from A, you have a high probability to reach B. So this is naturally captured by this notion of random walk, but it also works at distance higher than 1, because in your context, you also take into account the probability to reach nodes which are at distance 2 or 3 or 4, depending on the size of your context. So you see that your distance in the embedding is proportional to kind of the distance in the graph, and so it can be used for link prediction directly. So just to sum up, this is exactly as what we have done, like what we have done last week. You compute this distance in the embedding, and it's equivalent to what before we had computed with heuristics. So before you had, for instance, the number of common neighbors, and the pairs of nodes with the highest number of common neighbors was the pair of nodes most likely to become connected by an edge. With embeddings, you will compute the distance between each pair of nodes, and the pair of nodes which are the closest in the embedding are the most likely to become connected by an edge. The other approach is supervised link prediction, and again, it's the exact same process as last week, but this time, instead of using a vector composed of several heuristics, you remember last week we were composing a vector with common neighbors, Adami Kadar, preferential attachment, and so on and so forth. So we do exactly the same process, but this time we have a vector composed of automatically computed features, which are the dimensions of the embedding. So the problem is that until now we have computed vectors for nodes, and in this case we need features for pairs of nodes. And to compute these features for pair of nodes, there are several ways to combine vectors of the nodes. And there is not one which is, obvious, and the other one, so there are several possibilities that are used in the literature, and usually it's used as, a meta parameter, which is so you can try several of them and see which one works the best, and just keep this one. In the literature, it has been observed that usually it's the Adama product that works the best. So just to summarize them, a possibility is to take the average of the vectors of the two nodes at the extremity of the pair of nodes. You can concatenate them. So if you had a dimension, an embedding in 10 dimension for the nodes, for each head, you will have an embedding in 20 dimension. So Adama product is just to multiply each of the elements of the vector in sequence. So the first element of the vector of A and the first element of the vector of B, the second element of the vector of A multiplied by the second element of the vector of B, and so on and so forth. Or you could take also some notion of distance, also element by element of the vector. But again, there is not one which always works the best, even though often the Adama product seems to be the one that works the best. So you can use it to compute these embeddings for edges from the embeddings of nodes. So again, how well does it work? This is also a controversial problem, I think, because again, it's quite a recent topic. So if you refer to the papers of the authors introducing a method, like for instance here, it's from the paper introducing notch to vec. So they observed that they get higher scores, in AUC in this case, than heuristics. But the problem is that in the paper, they just compare to each heuristic independently, while we have seen that the best results usually they are obtained by combining these heuristics. So they observe that notch to vec is better than heuristics, but some other authors say that actually if you take more heuristics and you combine them, you get better results than notch to vec. So probably it depends on the network actually. So yeah, just in a paper we published in 2018, we tried to compute this, and what we observed is that it's actually different. So first, it depends if you use the AUC or the average precision. And if you use the average precision, it seems that heuristics are more obtain higher scores. And if you use the AUC, it also depends on the number of dimensions that you're using. So the more dimensions, the better the results. And we tested several methods, and for the methods we tested, it seems that one algorithm I haven't introduced here, which is called VERS, is indeed obtaining results which are better than the heuristics. But so this is just a small experiment. Yeah, so just to say a few words about this recent paper, which was published a few months ago. So you see, it's a topic which is it's actually a hot topic where, let's say, currently. And in these papers, the authors, they tested a lot of different approaches. So they tested topological heuristics. So you recognize here a list of what we have seen last week, like academic ADAR, preferential attachment, number of common neighbors, but they also used other one based on random walks and various others. They also tested a few embeddings. In particular, you see deep walk here. And they also tested model-based approaches, as I have described also last week, like the modularity, stochastic block models, and so on and so forth, and InfoMap, and so on and so forth. And they tested all these methods on a large number of different graphs, I think more than 500. And they compared, they grouped these graphs in categories. So, for instance, social networks, biological networks, economic networks, transportation network, and so on and so forth. And they observed what is the efficiency, the quality of the results obtained by each of these approaches on each of these categories of networks. And as you can see, the results are quite different. For instance, you see that these methods are very efficient on social networks, but maybe so embeddings will be more efficient on transportation network in that case, while the other one are not efficient on transportation networks. And so one of the key point is that the result really depends on the graph that you are analyzing. So what they proposed actually in this paper, so you see the title of the paper is a stacking model for nearly optimal link prediction in complex networks. And what they propose is some model that take all these different results and combine them in an efficient way to make the best possible prediction as possible. If you want to get an idea, it's a principle of voting. Each method try to vote for a prediction, and with these different votes, we learn how to combine the different prediction into the most efficient possible prediction. And in the results, so these are all the different methods, so modularity, InfoMap, stochastic block model, embeddings, and topological approaches, so heuristics. And they have shown that, so depending on the type of network, so this is overall for all the networks, and this is only for the social networks, they show that the results are quite different. So for instance, here you see that the AUC for embeddings is quite high, and it's actually higher than what they call model-based, so modularity, InfoMap, and so on. But in the end, it's their model, which is stacking all the possibilities, which is the best. You see, there was 97, while here it was only 95. And overall, for the whole network, they show that the topological approaches actually are very good. So heuristics actually get very high scores. And also combining topology and models like communities is also very efficient. And combining everything is not always the best, but nevertheless, it's a good way to find a good solution. This way to combine the prediction of the different models. There is also another type of embedding I haven't talked about yet, which is able to embed roles in the graph. So the idea of not2vec and deep walk is that the context which we collect by the random walk contain the labels of the encountered nodes. Okay, so we are doing this random walk, and we're starting from node N1, and then we encounter node N2. So in the sentence that we write N2. So N1, N2, N10, N15, N2, and so on and so forth. Okay, so this is the sentence we are generating. So the context of a node is composed of other nodes. But actually, instead of memorizing this label, we could memorize some properties of the nodes. So, for instance, if nodes have properties like age or revenue or anything, political opinion, we could memorize this information. Or we could also memorize some computed attributes like the degree, the clustering coefficient, whatever. So if you think of what's happening, we keep the label of the node from which we want to know the context. So we know that we're starting from N1, for instance. But in the context, we will find information. So we will find, for instance, degree 10, degree 2, degree 5, degree 10, degree 10, degree 3, and so on and so forth. And so when we will compare nodes, actually we will two nodes that will be considered similar will be nodes with the same context. And so nodes with the same context will be nodes with the same kind of nodes around them. So we don't care anymore about having the same nodes around. So two nodes that are similar do not have the same nodes in common in their neighborhoods, in their context, but they care of having the same types of nodes encountered in the same type of way with the same frequency around them. So again, if we have used some, for instance, political opinions, two nodes will have close embeddings if they encounter nodes with the same opinions around them. If we take degree or clustering coefficient, two nodes will have the same embedding if they encounter the same types of nodes around them. And so this is what we call detecting roles, actually, because, for instance, you can think that two nodes, for instance, that are in the center of a star, even if they are very far away in the graph, since they are centers of stars, they will have the same types of nodes around them, and so we'll have the same embedding or similar embeddings. So this corresponds to a kind of role. So maybe in this case, they are big players, so they are center of a star in the network. And so, for instance, in this in the paper of Structuvec, they have shown this example in which they have used two versions of the Zachary Karate Club graph. So here you have one version of the Karate Club. Here you have another version of the Karate Club. And they just added one edge between the same node in both graphs. And the objective is that now this node and this node should have a similar embedding in the whole graph because they occupy the same position. Same for this one and this one, and this one and this one, and so on and so forth. And so you see that they have used colors, color coding, so that we see that if in the embedding two nodes with the same color should be closed in the embedding. And this is the result using a Structuvec algorithm in 2 dimensions. And as you can see, these two nodes that have the same colors, they are indeed closed in the embedding. Same thing for this one, same thing for this one, this one, this one. So here it's a little bit more messy, but it's not really a problem because maybe it represents all these nodes that occupy a position which is not well defined. While these nodes are quite important, so I think they are the instructors of the Karate Club, this one and this one, that occupy very specific position. And indeed, their roles are close. The vector representing their roles are very close. Same thing for this one that occupy also maybe an important position. It's again maybe some sort of being at the center of a star. So yeah, so you see that this approaches is relatively simple. It's a simple modification of the deep work mechanism, but it captures really something which is different, and you can see that it can be really useful. For instance, for node classification, probably not for link prediction, because now we are not really considering that these two nodes are close in the graph, so are likely to be connected. But rather, if I want to predict, I don't know, for instance, a label that will be instructor, being an instructor, it doesn't really help to know that they are in the same part of the graph, but it really helps to know that they have a similar role.